All right, so this is a video that actually got sidebarred for a while, and I forgot about it, but I'm going to be doing it right now. And this is the solution to the stack boxes and friction problem. Okay, so this problem says, it says a block. Somehow I edited this. A block of mass M1 is at rest on a table. A block of mass M2 is stacked on top of it. Coefficient of friction between the blocks is mu1, and the coefficient of friction between M1 and the table is mu2. A horizontal force, a force horizontal, needed to be edited, is applied to M1. Okay, so we want to follow the problem-solving strategy in order to obtain a system of equations to describe the motion here. And so the first thing that we want to do is draw a free body diagram. Okay, so here we have our blocks here. And before actually we draw a free body diagram, because there's not a picture given, we're going to draw the system here. So we have a block of mass M1. It's at rest on the table. So here's our table. And then a block of mass M2 that's on top of it. And there is a coefficient of friction between these. This is going to be some mu1. And then there is this coefficient of friction between the block M1 and the table. This is going to be mu2. We're applying a horizontal force to M1 like this. Okay, so this is going to be our applied force. Okay, so first part here, we want to draw a free body diagram for each one of these. So if we look at the block M2, here's M2. We have gravity acting on it. This is M2G. We have a normal force that is acting from block 1. So I'm going to call this N12. And there's going to be a force of friction going to the right, because that's actually what's making this go, right? So this is the force of friction between block 1 and 2. So this is the force of friction block 1 acts on block 2. And then we have our block M1 here. So M1 is going to have some normal force from the table. We're going to call this N1. We have some N21. So the normal force that block 2 acts on block 1 acting on this, right? Because they're stacked on top of each other. There's a pair of Newton's third law forces that act between these, equal and opposite, right? So we have the one that N1 acts on, the one that M1 acts on M2, and the one that M2 acts on M1, but they're equal and opposite. We also have gravity, so this is going to be M1G. We have our applied force that's going to be going like this. We actually have two forces of friction. We have the force of friction that block 2 acts on block 1. Again, this is a pair of Newton's third law forces, so they're equal and opposite. And then there's the force of friction that's just acting on this block. Okay, so those are our free body diagrams. So the next thing that we want to do is we want to obtain a system of equations to describe the motion here. And so to do that, we're going to break this into two parts. We have the block 1. So we're going to sum our forces. It's going to be equal to M1A. Sorry, that's not a mass vector. It's an acceleration vector. And this means sum of the forces in the x direction is going to be equal to M1AX. Sum of forces in the y direction is going to be M1AY. And so in doing this, we realize that we need a coordinate system here. So I'm going to draw our coordinate system. There's our x direction and our y direction. Okay. So summing the forces in the x direction, this is going to say this is going to be equal to the applied force minus the force of friction that the table acts on the block, minus the force of friction that the other block is acting on this. Okay. Summing the forces in the y direction says this is going to be equal to N1 minus N2, N21 minus M1G. And this one happens to be equal to 0 because the acceleration is going to be 0. Okay. So that's 0. Okay. So for our second block, sum of forces is equal to mass times acceleration. Sum of the forces in the x direction is going to be equal to M2AX, which is going to be equal to, actually this one only has one force. This is the force F12. Sum of forces in the y direction is going to be equal to N12 minus M2G. And this one, again, is equal to 0 because the acceleration is going to be 0. Okay, so the next thing we want to do is solve for N12 and solve for N1. That's the next portion that we have here. And so when we do that, this is part B. So part B is basically just take this equation and this equation right here and solve for n1 and n12. So for the bottom equation, what we end up finding is that n12 is going to be equal to m2g. And from the top equation, we end up seeing that n1 is going to be equal to m1 plus m2 times g. Okay, so that's part B and C, actually. So we have part B and C. And then the next part that we want to find is we want to find the acceleration of the system. Okay, so in order to find the acceleration of the system, what we want to do is we want to look at our equations in the x direction here. Right, so we did the equations in the y direction in order to find what the normal forces are, but now to find the acceleration, we're going to do the sum of the forces in the x direction. And so when we do this, we end up seeing that this is going to be, I'm going to rewrite this, so this is going to be part D. We have F12 is going to be equal to M2AX, and then we have, this is going to be the force applied minus F21 minus F1 is going to be equal to M1AX, okay? Now, the trick that we can apply here is we can just add these vertically, okay? It's just a trick to do the algebra quickly because of, ultimately because of Newton's third law, because the force F12 is the same as the force F21 in terms of the magnitude, but they're opposite in direction, which is shown in this equation here. And so what that says is these guys cancel each other, and so ultimately we're going to have Fa minus F1 is going to be equal to M1 plus M2 times AX, okay? Almost there, but we have this F12 that we have to deal with, or this F1 that we have to deal with. And ultimately, F1 is going to be equal to, and this was the part that I think confused some people because I should have chosen this a little bit better, but this is going to be mu2. So this is going to be mu2 times n1. Yeah, I should have done this in terms of mu1, but I flipped these in the definition here. So per the way I had originally defined it, this was going to be mu2. And so then what that means is I can take this and I can plug it into this equation, noting that we know what n1 is going to be because we solved for it up here. And so doing that and rearranging for ax, we end up seeing that ax is going to be equal to 1 over m1 plus m2 times the applied force minus this is going to be mu2 times m1 plus m2 times g, okay? And that is our acceleration of the system, okay? When this is moving, okay? Now let's look at the next portion. So the next portion is determine expression for the force of friction acting between the blocks if it is small enough that m2 does not slip off the table, okay? So M2 doesn't slip off of M1. So this is really important when you're talking about friction, because you never want to say that the force of friction is going to be mu times n. Or you don't want to generally say that's true. You always want to say that the force of friction is going to be less than or equal to mu times n. Okay? This is the maximum value you can have. And we know that in the previous portion, when I said it was explicitly mu2 times n, it's because it was taking on its maximum value. But this case right here, when we're looking at the blocks that are stacked on top of each other, what we're going to say is that this force of friction here is not equal to mu times n. It's just equal to the mass m2 times the acceleration in the x direction. And we found that already. So we found that when we plug in this ax here, this force of friction, F12, is going to be equal to m2 times ax, which is going to be equal to m2 over m1 plus m2 fa minus mu2 m1 plus m2 times g. Okay, so this is what the force of friction is when it's below its maximum value. But now we're going to be looking at the case where it takes on its maximum value, and that's the last question here, is what is the expression for mu2. And sorry, this was actually originally supposed to be mu1. So I'm going to edit this this question so that it reflects what we need to. But what is the expression for mu1 when it's about to slip? And so that's to say now we're not talking about F12 is less than mu1 times n2. We're saying that F12 is equal to mu1 times n2. And so effectively what we do is we just take this equation and we plug it in there. Okay? And so when we do that, what we end up seeing is that mu1 times m2g is going to be equal to m2 over m1 plus m2, fa minus mu2 m1 plus m2 times g. And then we could rearrange this if we wanted, so we can cancel our m2. And effectively what that means is I'm going to bring a 1 over g over here. So we got a 1 over g factor here, and then we cancel this and this and this, and so then this is going to be a 1. And to rearrange this so that's in a nice spot here, we can say that that is going to be what u1 is. Okay. So important takeaways from this: force of friction not always equal to mu times n. It's equal to mu times n when the object is in motion, and when the object is in motion, the force of friction is taking on its maximum value. But in the case of these blocks, when I'm talking about it being in motion, I'm not talking about motion at all. I'm talking about relative motion, right? So m2 is stacked on top of m1, and so if it's not moving relative to m1, so it stays on top of it, that means that the force of friction is going to be at or below its maximum value. And in the case of this part, E, in the case of E, then it's not going to be its maximum value of mu times n. And then in part F, we're actually trying to find what is the case where it is equal to its maximum value. What's the expression that we have for what the coefficient of friction is going to be? Okay, so that one's going to be it. Take it easy, guys. Good luck studying.